thank you. So I'm going to talk about our work at Sandia on designing analog crossbar accelerators. All right, so why do we want an analog accelerator? And it really just comes down to data movement. So if you look at current transistors, they're already getting pretty efficient, only 10 attojoules compared to your 40 kT noise limit of 0.2 attojoules. But now you look at what's the energy just to move a bit from one end of the chip to the other, and that's on the order of a picojoule, 5 orders of magnitude more. So that's our huge opportunity. Any sort of traditional computing has this memory and processing separation, and any sort of data movement becomes very, very expensive. And you can try improving that, going to photonics and things like that, but you're still going to end up on that 100 femtojoule to 1 picojoule bit to move your data around. So the question is, how do we reduce that data movement? And so the key is that we really want to process in the memory itself, so you can get rid of much of that movement altogether. And how do you do that? Well, we want to just use an analog ReRAM, or basically a programmable resistor. So if you look at Ohm's law, V equals IR, that's a multiplication operation. Or if you flip it, the current equals the conductance times the voltage. And now if you want to do addition, you just add two currents together, and that's a summation operation. And so what's a ReRAM? That's just a programmable resistor. And so the way it works essentially is if you apply a large voltage, you cause some ions to move, your resistance changes. If you apply a small voltage, you can read it out and read the conductance. And so now the key is that with these analog kernels, you can actually do matrix operations directly in your memory. So here you can do a vector matrix multiply. So you apply voltages on your rows, read the currents out. And you can see that you're doing all your computation directly in place. And so you're essentially parallelizing the readout of the whole memory array. And now an important part is we want to do a training accelerator. So we don't just want to do the vector matrix multiply. We also want to be able to write the whole array in parallel. And so the key for that is to be able to do an outer product update. The idea is that you want to update each weight by the product of the signal on the row and the signal on the column. So that each weight can be changed. And these two together form the kernel of many different neural network algorithms. And so one more thing to mention is the energy scaling for each of these arrays essentially scales as the number of elements. So to read out the entire array or write the entire array just scales as the order of n squared for an n by n array. Now this is very different than any sort of digital memory. To read out any digital memory, you have to go row by row. And what that means is that to read out this row, you have to charge all of the columns, all n columns. And so now you have to do that n times for the n rows. And so what that means is that accessing a digital memory is fundamentally order n worse than any sort of analog readout. And so then that gives us the key advantage of why we want to do analog. And that's just ignoring the multiplication and all of those benefits as well. This is just the data movement of trying to get data out of your memory to a processing unit, even if you put it right next to it. All right, so now we'd like to design an accelerator that can accelerate many different algorithms, not just backpropagation, but in addition, perhaps sparse coding, liquid state machines, some of the things like the Boltzmann machines, or simulated annealing type accelerators. So what's in common with all of these algorithms? And the key comes back again to these matrix operations, the vector matrix multiply, and the outer product update for the training. So how do we build an accelerator around this? And so this architecture that we're looking at is that we have a neural core to accelerate the matrix operations. So if an n by n matrix, you're accelerating order n squared operations. And now you have order n inputs and outputs that will process in digital. And the idea here is that we can spend more energy and time on the inputs and outputs because there's only order n of them. But that gives us the flexibility to look at all of the different learning algorithms while still accelerating the bulk of the computation, the matrix operations. And so you can kind of see how this would work for a neural network. If you have your synapse operations, which is essentially a vector matrix multiply, is order n squared that we do on a crossbar, and then we process our neuron in digital, which is order n. And you can do the same thing for the training. All of the vector matrix multiplies are done in the crossbars, your write or your outer product updates done on the crossbar, and then sort of these are all the matrix operations. And now the vector operation is computing what the update should be. And so that's done in digital. And now this gives you the flexibility to try many different learning algorithms and to use the different advanced neural network techniques to do your training. So now we've kind of seen that on a sort of a scaling point of view, why should a crossbar be better? The question is, does it actually hold when you go through and look at a particular system and try to design it out? And so now we're looking at just the neural core kernel And so we went through and designed all the analog to digital converters, the digital to analog converters, doing all of the analog circuitry. And we want to see how does this compare to an optimized digital accelerator. That being that you have a digital memory, either SRAM or digital ReRAM, directly next to a multiplier. And so we go through, we design the circuitry, and what we find is that we can get 100 to 1,000x benefit in energy and latency and about 10x in area. And so there's a couple things I want to point out here. So first is that the energy benefit depends very much on what sort of bit precision we need coming in and out of the crossbar. Because if you have an analog to digital converter, that's going to be expensive. So at 8 bits, we're getting around the 100x benefit. But if we can reduce our inputs to 4 bits or 2 bits, then we can get up to the 1,000x benefits. And then, so we already saw the energy is sort of coming from the data movement, and that's why we're getting that benefit. The latency just comes from the parallelism. 1,000 by 1,000 crossbar is doing 1,000,000 matrix operations, or 1,000,000 computations in one step. And the area is 10x, is not actually as good as we would have expected just from the ReRAM density alone. And that's because the ReRAM is actually only about 10% of the area of our accelerator core. It's all the analog circuitry that dominates the area. And so if you look at the energy breakdown in a bit more detail, or actually before that, one more point I just want to emphasize is that this assumes that we have high resistance 10 to 100 mega ohm devices. And that's just because we want to be able to do a 1,000-fold parallel operation. So if each device is passing just 10 nanoamps, multiply that by 1,000, you're at 10 microamps, which is around your limits of a scaled wire. And so a key thing that we need is high resistance devices. And so now looking at the energy breakdown, and you can see in the analog for the 8-bit system, it is the analog to digital converter that's dominating. And it's not until we get down to 4 or 2 bits that the energy is more balanced, where all the other components are about equal. And now if you look at the digital accelerators, there's 2 components that dominate the energy: the multiply and accumulate, and just data movement from the SRAM memory bit to the edge of the SRAM array. And what's great is in analog, both of those are free. And so you've eliminated the bulk of your cost, and so that's why we're getting this 100 to 1,000x benefit. All right, so we're kind of seeing that in an architecture energy level, how there could be a benefit. But the problem is these are analog devices, they're noisy. The actual properties of the device are now going to impact the accuracy of your training algorithm, of your learning algorithm. And so now, unfortunately, this means we're going to have to be designing from like our materials properties can now affect our algorithm design. So this becomes a very difficult co-design problem. If you think about the power of VLSI, is that computer programmers don't even need to know what a transistor is. And similarly, transistor designers don't have to care about any of the latest or greatest programming languages. And now it seems like we're losing some of that abstraction. Your actual device properties can impact the algorithms. So how do you do this co-design? And so to enable that, we've created the software. It's fully open source. If you're interested, I suggest you download it, try it out. But the basic idea is we want to make as much abstraction as possible. So an algorithm designer can build their learning algorithm on top of matrix operations: vector matrix multiply, the transpose matrix vector multiply, and then outer product update. And then the simulator will, based on a given device model, can model how does the device impact the accuracy of your algorithm using either a numeric model, slower but more accurate circuit simulations, and we're working on actually doing interfacing with physical hardware crossbars. So here, just kind of to reiterate kind of the idea of creating this abstraction. The idea being that you specify your device properties through some settings, and then you build your entire algorithm just around the matrix operations without worrying about the device at all. So this way, device people can just worry about getting their device properties and then just put it in here and see how it performs on a neural network. Similarly, algorithm people can just focus on developing the algorithms and then see how different devices impact it. So here, going through that process, this is an example of us going through that process for tantalum oxide ReRAM devices that we fabricated. First, we build the device, then we measure the device by applying a series of pulses, seeing what the conductance changes, and collecting statistics. So now say you start at its given conductance, and then you see what's the conductance change and what's the spread. From that, you get a probability distribution, and then putting that into our simulator, you can assume a certain crossbar model, and then build a neural network on it and see what your training accuracy is. Now you look, for this plain tantalum oxide device, it's actually not that accurate. Ideally, we'd be getting around 98% accuracy, and it's only coming out to around 80%. And so that tells us we have a ways to go. And you can kind of see why. Is that as you start different conductances, you're writing different amounts. And then you have noise where if you apply a pulse here, we want to get a positive change. Sometimes you get a negative. So it's a very noisy device. So how do we get around that? So there's a couple of things. One is now that we have the simulation framework, we can start looking at new algorithms that can take advantage of these devices. And so one idea is that, well, if we need more levels, let's just use more devices per synapse. Now, ideally, we'd want to use something like a base 10 system. So you could have 10 devices representing 1 through 1,000. Now, the problem is, of course, when you try to do a carry, or when you try to write, say, some device that's at level 9, that means that you have to reset the 9 to a 0 and then increment the 10s. And this prevents a parallel write. Because a parallel write assumes you don't know your state and you just blindly apply a write pulse to your devices. And so if you try to use a base 10 system, that's not compatible with doing a parallel write. And if you can't do a parallel write, there's no point in doing the analog for training. So the question is, how do you get around that? And the key is simply that you want to have some extra levels to store the carry. So now when you're at 9, you can go to 10, 11, 12, and then every few hundred cycles, you do the carry. So you can average out the cost of performing a carry. And that lets you get the benefit of both the parallel writes and the base 10 type number system. And so you can see that this helps with the noise. So if you had a device where your noise is larger than your individual updates, if you try to train a single device, you would have no idea what you're learning. But with the periodic carry, you can learn what the weight's supposed to be. Similarly for nonlinearity. And so now this, I want to kind of emphasize, is one of the things that kills these neural networks more than even the noise. And that's that if you apply a series of write pulses, identical pulses, you reach some maximum weight or maximum conductance. And if you apply an opposite pulse, you get a large change. And so you lose all your training from the previous 5 or 10 pulses. And so this causes weight decay. So let's say we've trained a weight up to 10, and now our network's more or less trained, but just through the noise and the input images, we have some oscillating pulses that should be oscillating back and forth, but staying around 10. But this nonlinearity causes the weight to decay to 0, and so you actually lose your learned information. And so that kills the accuracy of trying to train a neural network. And so fortunately, the periodic carry also helps with that. With a single device, you wouldn't learn anything. Your weight decays to 0. With this, if we're trying to learn 0.6, instead we learned 0.2. So it's not as good, but as you train over multiple learning cycles, it'll just take longer, but you'll eventually get the information. And so now you can see that noisy tantalum oxide device that only trained to 80% accuracy can now get up to around 97% accuracy on MNIST, which is recognizing handwritten digits. It's only 1% away from the ideal. And so now, last thing I want to mention is that in addition to looking at algorithm levels, we can also look at developing new devices. So our material scientists at Sandia have come up with this idea that you essentially take a lithium-ion battery and put a source and drain on the cathode. Now, as you charge or discharge your battery, you change the resistance of your cathode, and thereby changing the resistance of the device. And this is nice because it ends up being very linear, very low noise. And so just the device by itself can train to very high accuracies, only 1% away from that ideal. And so it has some challenges. It's still relatively slow. It has some retention challenges. And so we're working on improving that, looking at new materials. But it's an interesting direction to explore. So to summarize, the analog accelerator can give you 100 to 1,000x benefits in energy and latency. And it really comes from that fundamental order and scaling advantage. You don't have to move your data out of the memory. And now, but designing is very difficult when you have to design from materials to algorithms. So we've developed this open source software across them to allow you to do that. And you can use that to benchmark new devices and to develop new algorithms like periodic carry. And lastly, for the device people, if you're looking, what device properties do I need? The things I would focus most on are we want higher resistance devices to allow for more parallelism. And we want low write nonlinearities. Even more than the noise, that's what ends up hurting the training accuracy. Thank you.
Okay, this paper is now open for questions. Go ahead, Eli.
You had an advantage over conventional digital accelerators because there was less data movement because you didn't have to move all the way to the edge to get the data and bring it back. But this morning, we heard that the next big trend is going to be three-dimensional, where the data storage is just above the switches. So it seems like maybe they can compete with you. What do you think of that?
to some extent, but they're still going to have some sort of memory array. Whether you're stacking through 10 levels, 100 levels, you're going to have to move it all the way through your memory to where your computation unit is. Because you still can't have an adder next to every single memory bit. You're still going to have some density of memory. And so you still have some amount of movement.
Okay. Did I see another question? Yeah.
So the resistance requirement doesn't sound in line with conventional RRAM resistance.
So there have been demonstrations of devices at this high resistance. The challenge is that the analog properties haven't been measured, or it's not well known. And so we're looking at that. And so there are devices, but not with the high resistance and the good analog.
Okay. Yeah?
Quick question.
Here we go.
It's a quick question. Is this large-scale fabricatable? Is it currently compatible, making those memory ReRAM compatible with the current foundry process? And
Yeah, great question. And so that's one of the big advantages of ReRAM, is that it's fully back end of the line compatible. You can put it directly on top of your transistors in the back end of the line processing, and so integrate it without taking up additional area.
You made a big fuss about the saturation of the resistance value. Isn't that something that's just peculiar to memristors? And aren't there lots of other analog memories that you could use that wouldn't be suffering the saturation to the same degree? I mean, you mentioned the use of lithium-ion battery technology, but I can imagine that flash memory can also maybe not be so subject. It'll saturate eventually, but there are ways of dealing with that.
So I agree. I mean, we definitely need to start looking at other technologies as well. And so we've done some experiments on flash, and it does still saturate, but you have a much larger on-off ratio, so you can potentially pick an operating range. And you're right. I think that's part of it, is looking for new devices that don't have that issue.
Okay. So let's thank the speaker again.
Thank you.